Section. Introduction. Let's dive into the world of large language models, LLMs. These models often use the same prompts repeatedly. For instance, they might start with the same system messages that explain how they work. They might also use the same documents in different prompts. This is especially true in fields like law, healthcare, and education, where a prompt might include one or more documents from a set. Prompts can also be formatted using reusable templates, which is common in robotics and tool learning. This leads to a lot of text overlap between prompts that use the same template. To address this, we've come up with a new technique called prompt cache. This technique is based on the fact that the prompts used by LLM servers often share components in a very structured way. The main idea is to pre-calculate the attention states of the parts of the prompt that are used frequently and store them in memory for future use. Reusing attention states is a common way to speed up the service of a single prompt. The current method, known as key-value (KV) cache, reuses the key-value attention states of input tokens during the autoregressive token generation. This means that we don't need to calculate full attention for every token generation. By storing the key-value attention calculated for the previously generated token, we only need to calculate key-value attention states once for each token generation. Prompt cache builds on this by extending attention state reuse from a single prompt to multiple prompts. It does this by making attention state reuse modular. In our approach, we pre-calculate and store the attention states of frequently reused text segments individually. When these cached segments appear in the input prompt, the system uses the pre-calculated key-value attention states from memory instead of recalculating them. This means that attention calculations are only needed for uncached text segments. However, reusing attention states across prompts presents two challenges. First, attention states are position-dependent due to the positional encoding in transformers. This means that the attention states of a text segment can only be reused if the segment appears at the same position. Second, the system needs to be able to quickly identify a text segment whose attention states might have been cached so that it can reuse them. To overcome these challenges, prompt cache uses two strategies. The first is to make the structure of a prompt explicit with a prompt markup language, PML. PML makes reusable text segments explicit as modules, which not only solves the second problem but also helps to solve the first, as each prompt module can be assigned unique position IDs. The second strategy is based on our finding that LLMs can operate on attention states with discontinuous position IDs. This means that we can extract different segments of attention states and combine them to create new meanings. We use this to allow users to select prompt modules based on their needs, or even update some prompt modules during runtime. In practice, an LLM user writes their prompts in PML, with the intention of reusing the attention states based on prompt modules. They must derive a prompt from a schema, which is also written in PML. When prompt cache receives a prompt, it first processes its schema and calculates the attention states for its prompt modules. It then reuses these states for the prompt modules in the prompt and other prompts derived from the same schema. We've implemented a prototype of prompt cache on top of the Hugging Face Transformers library. While prompt cache can work with any transformer architecture compatible with KV cache, we've tested it with three popular transformer architectures powering the following open-sourced LLMs: Llama 2, Falcon, and MPT. We've considered two types of memory for storing prompt modules: CPU and GPU memory. While CPU memory can scale to terabyte levels, it brings the overhead of host-to-device memory copying. In contrast, GPU memory does not require copying but has limited capacity. We've conducted an extensive benchmark evaluation to examine the performance and quantify the accuracy of prompt cache across various long context datasets. We used the long bench suite, which includes recommendation and question answering tasks based on multiple documents. In our evaluation, prompt cache reduces time to first token latency from 1.5 times to 10 times for GPU inference with prompt modules on GPU memory and from 20 times to 70 times for CPU inference, all without any significant accuracy loss. We also analyzed the memory overhead of the precomputed attention states for each model and discussed ways to optimize the memory footprint of prompt cache. We then demonstrated several generative tasks, including personalization, code generation, and parameterized prompts, to show the expressiveness of the prompt schema and performance improvement with negligible quality degradation. In this study, we mainly focused on techniques for modular attention reuse. However, we believe that prompt cache could be used as a foundational component for future LLM serving systems. These systems could include enhanced prompt module management and GPU cache replacement strategies, optimizing the advantages of both host DRAM and GPU HBM. Section Summary. The authors introduce a technique called prompt cache to reduce the computational overhead in generative language models. Prompt cache precomputes and stores frequently reused text segments in memory, allowing the system to reuse attention states instead of recomputing them. By leveraging a prompt markup language, PML, and the ability of language models to operate on attention states with discontinuous position IDs, prompt cache enables users to select and update prompt modules based on their needs, resulting in improved performance without significant accuracy loss. Section. Background and related work. Our work on prompt cache is built upon the principles of the key value, KV, cache, which is a method used to speed up the process of generating tokens in language learning models, LLMs. In this section, we'll discuss how autoregressive token generation works in LLMs, how the KV cache can make this process faster, and how it's been used in recent research. We'll also touch on other methods used to speed up LLM inference. In autoregressive token generation, an LLM starts with an initial input, often referred to as a prompt, and generates the next token based on this prompt. This token is then added to the prompt and used to generate the next token. This process continues until a certain condition is met, such as reaching a predetermined number of tokens, generating a special end-of-sequence token, or achieving a satisfactory level of coherence or completeness in the generated sequence. The model uses the entire prompt and all the tokens generated so far as input at each step. The KV cache is a technique used to reduce the computational load of this process. Normally, the model would need to compute the key and value embeddings for each token at every step of the autoregressive token generation. But with the KV cache, these embeddings are computed only once and stored in memory for future use. This means that instead of recalculating the attention states for each token at every step, the model can simply reuse the cached values. This significantly reduces the amount of computation required. To give you an idea of how this works, let's say we have a sequence of n tokens in a user prompt, and we're generating k additional tokens. In the traditional method, the attention states for all these tokens would be recalculated at every step. But with the KV cache, the attention states for the initial input are computed and stored in memory. Then, for each subsequent step, the model reuses these cached values to compute the attention state of the new token. After each step, the newly computed attention states are added to the cache for future use. This method does come with a trade-off. It sacrifices precision for computational efficiency. Instead of computing the attention state for a token over the entire sequence, the computation is limited to the sequence available at that step. However, empirical results have shown that the quality of the output is largely unaffected, making the KV cache a popular choice for LLM systems. The KV cache has sparked further research into speeding up LLMs. Some studies have focused on improving memory management for the KV cache, while others have looked at pruning unnecessary KV cache data or compressing it. Some preliminary work has also explored reusing the KV cache across different requests. In addition to the KV cache, there are other methods used to make LLM inference more efficient. For example, some systems use multiple GPUs for inference, while others use high-performance GPU kernels for softmax attention score computation. Our current focus is on achieving low-latency inference in LLMs, but our work on prompt cache could also benefit systems aiming for high throughput. The success of the KV cache led us to ask, can attention states be reused across multiple inference requests? We noticed that different prompts often have overlapping text segments. For instance, the same system messages or metaprompts are often inserted at the beginning of a prompt to elicit desired responses from an LLM. In many legal and medical applications of LLMs, the same set of documents is often provided as context to different prompts. And in robotics and tool learning applications, reusable prompt formats or templates are commonly used. This observation led us to develop prompt cache, a method that improves computational efficiency by reusing attention states across multiple requests. This is done by taking advantage of the text shared by prompts. Section Summary. Prompt cache is a technique that improves the efficiency of autoregressive token generation in language models by reusing attention states across multiple inference requests. It builds on the idea of the key-value cache, which computes key and value embeddings for each token only once during token generation. By reusing cached values, the computation required for self-attention is significantly reduced, resulting in faster inference without sacrificing output quality. Section. Overview. We're going to simplify and explain the given text in a more understandable way. The main idea here is about the attention states of a text segment in a language model. These attention states can only be reused if the text segment appears in the same position in the model's input. This is due to the way transformer architectures work, as they incorporate positional information into the attention states. This isn't an issue when we're dealing with a single prompt, as the same text is always at the beginning of the input. However, when we have shared text segments that can appear in different positions in different prompts, reusing their attention states becomes a challenge. To overcome this, we need a system that can recognize and reuse attention states, even when the text segment appears in different positions. We propose two solutions for this. First, we introduce a prompt markup language, PML, which makes the structure of a prompt explicit. This allows us to identify reusable text segments as modules and assign them unique position IDs. This not only helps us recognize and reuse attention states, but also allows us to handle text segments appearing in different positions. Second, we've observed that language models can work with attention states that have discontinuous position IDs. This means we can extract different segments of attention states and combine them to create new meanings. Even if these combined attention states miss some position IDs, the output quality isn't affected as the relative positional semantics are still retained. We use these two ideas to create a system called prompt cache. Here's how it works. A user writes their prompts in PML, intending to reuse the attention states based on prompt modules. They must create a prompt from a schema, which is also written in PML. When prompt cache receives a prompt, it processes its schema and calculates the attention states for its prompt modules. These states are then reused for the prompt modules in the prompt and other prompts derived from the same schema. This approach is similar to locally masked attention, which optimizes computations by limiting the window for attention score calculations. In prompt cache, each prompt module is encoded independently, and attention states are calculated within the confines of the prompt module. This is like an attention mask that screens out sequences external to the prompt module. We also introduce the prompt markup language, PML, which is used to describe both schemas and prompts. A schema is a document that defines prompt modules and outlines their relative positions and hierarchies. Each schema has a unique identifier and designates prompt modules with the less than module greater than tag. Texts not enclosed by less than module greater than tags are treated as anonymous prompt modules and are always included in prompts that use the schema. A user can construct a prompt from a schema with the less than prompt greater than tag. This tag specifies the schema to use, lists the prompt modules to import, and adds any additional instructions. For example, to import the module, Miami, from the schema, one would express it as less than Miami, greater than. PML also allows a prompt module to be parameterized to maximize reuse opportunities. A parameter is a placeholder with a specified length that can appear anywhere in a prompt module in a schema. When a prompt imports the prompt module, it can supply a value to the parameter. This is especially useful for templated prompts. In summary, we've proposed a system that allows for the efficient reuse of attention states in language models, even when text segments appear in different positions. This system, called prompt cache, uses a prompt markup language, PML, to make the structure of prompts explicit and to allow for the parameterization of prompt modules. Section Summary. The prompt cache system allows for the reuse of attention states in language models by using a prompt markup language, PML, to make the structure of a prompt explicit. This enables the recognition and efficient reuse of text segments across different prompts, even if they appear in different positions. Additionally, PML allows for parameterization of prompt modules, maximizing the opportunities for reuse and customization in prompts. Section. Other features. We're going to discuss some additional features of our system, starting with union modules. These are used when we have several prompt modules that can't be used together. Only one can be selected at a time. For example, If we're asking our language model to recommend a book based on a reader's profile, we might have several different profiles to choose from, but we can only use one at a time. We use a special tag, called a union tag, to group these modules together. This helps us keep our layout organized and makes our system more efficient. Next, we have nested modules. These allow us to create a hierarchy of prompt modules, where one module can include other modules or unions as components. This gives us a lot of flexibility in how we structure our prompts. We also have a feature that helps us format conversations for instruction-tuned language models. These models often use specific templates for their conversations, so we've introduced special tags to help us match these templates. These tags are used for system-level prompts, user-generated prompts, and responses generated by the language model. Now, let's talk about how we encode our prompt modules. The first time we need to use a prompt module, we have to compute its attention states. We do this by extracting the token sequences from the schema and assigning position IDs to each token. The starting position ID is determined by where the prompt module is located in the schema. For example, if we have two prompt modules before the one we're encoding, and they have 50 and 60 tokens respectively, our new module would start at position 110. We handle union modules a bit differently. Since all the modules in a union start from the same position, we consider the size of the largest module when assigning position IDs. Once we have our token sequences and position IDs, we pass them to the language model to compute the attention states. We also have a system for encoding parameterized prompt modules. These are modules that have placeholders for parameters, which are replaced with specific values when the module is used. We replace these placeholders with a special token, and log the position IDs for these tokens so we can replace them later. When we use the module in a prompt, we replace these tokens with the supplied arguments, and update the attention states accordingly. Finally, we have a system for caching inference. When we get a new prompt, we first check it against our schema to make sure it's valid. We then retrieve the attention states for the prompt modules from our cache, compute the states for any new text segments, and combine them to get the attention states for the entire prompt. This process is efficient and helps us reduce the time it takes to generate the first token. Section Summary. The paper introduces the concept of union modules, which allow for mutually exclusive prompt modules to be selected within a set. It also discusses the use of nested modules to express hierarchical prompt structures and the compatibility of the prompt cache with LLM-specific templates. The encoding schema of prompt modules is explained, including the computation of attention states and the handling of parameterized prompt modules. The paper also describes the process of cached inference, where the prompt cache retrieves attention states for imported prompt modules and computes attention states for new text segments to generate the attention states for the entire prompt. Section: Implementation. We've developed a prototype called Prompt Cache using the Hugging Face Transformers library in PyTorch. This prototype, which consists of 3,000 lines of Python code, is designed to integrate smoothly with an existing language model codebase and reuse its weights. We've made sure that Prompt Cache can utilize both CPU and GPU memory to store prompt modules, and we've tested it on both platforms. When it comes to storing these prompt modules, we use two types of memory: CPU memory and GPU memory. We use the PyTorch memory allocator to manage tensors across both types of memory. We've also made it possible for GPUs to access prompt modules stored in CPU memory by copying the modules from the host to the device as needed. This does create some overhead, but it also allows the GPU to take advantage of the large amount of CPU memory, which can scale up to terabytes. We've found that the computational savings from using prompt cache more than make up for the latencies caused by these memory copy operations. We've also had to adapt transformer architectures to implement prompt cache. This required support for discontinuous position IDs. While the Transformers library doesn't currently offer this feature, we were able to integrate it with minor modifications. For example, we only needed to add about 20 lines of additional code for each language model. We've also created lookup tables for each rotation matrix, which allows us to retrieve based on position IDs. This is used in models like Llama 2 and Falcon, which use rotation matrices for positional encoding and attention computations. In models like MPT and Bloom, we've designed a lookup table to adjust the bias matrix according to the provided position IDs. We've evaluated prompt cache by focusing on 3 research questions. First, we've looked at the impact of prompt cache on latency and output quality on extensive language model datasets. Second, we've analyzed the memory storage overhead of prompt cache on a per-token basis. Finally, we've demonstrated a set of language model applications where prompt cache can have a significant effect. We've used 2 CPU configurations for our evaluation: an Intel i9-13900K with 128GB DDR5 RAM at 5600 MTS and an AMD Ryzen 9 7950X with 128GB DDR4 RAM at 3600 MTS. For our GPU benchmarks, we've used 3 NVIDIA GPUs, the RTX 4090, which is paired with the Intel i9-13900K, and the A40 and A100, both virtual nodes hosted on NCSA Delta, each provisioned with a 16-core AMD EPYC 7763 and 224GB RAM. We've used several open-source language models, including Llama 2, CodeLlama, MPT, and Falcon. We've used models that fit within the memory capacity of a single GPU, 40GB. We've used the Long Bench suite to assess improvements and output quality changes. Long Bench includes a curated subsample of elongated data, ranging from 4K to 10K context length, excerpts from 21 datasets across 6 categories, including tasks like multi-document question answering, summarization, and code completion. We've measured the latency on both GPU and CPU using Llama 7B. In our GPU evaluation, we used 2 memory setups, storing prompt modules in either CPU or GPU memory. For CPU experiments, we used CPU memory. Due to space constraints, we present only 8 benchmarks. The complete benchmark can be found in the Appendix A. Section Summary. The authors implemented a prompt cache prototype using the Hugging Face Transformers library in PyTorch, which can seamlessly integrate with an existing LLM codebase and store prompt modules in both CPU and GPU memory. They also made modifications to support discontinuous position IDs and created lookup tables for embedding tables, rope, and alibi. The evaluation of prompt cache focused on its impact on latency, output quality, and memory storage overhead, using various CPU and GPU configurations and benchmark datasets. The results showed improvements in time to first token latency on both GPU and CPU setups. Section: GPU inference latency. We've conducted a study on the latency of GPU inference, and our findings are summarized in a figure. We used 3 NVIDIA GPUs for this study, the RTX 4090, A40, and A100. The yellow bars in the figure represent the time it takes to load prompt modules from the CPU memory, while the blue bars represent the same process but in the GPU memory. We noticed a consistent trend in latency across all datasets, as the samples from the Long Bench have similar lengths, averaging around 5,000 tokens. We found significant reductions in the time it takes for the first token to be generated, TTFT, across all datasets and GPUs. These reductions ranged from 1.5 to 3 times when using CPU memory, and from 5 to 10 times when using GPU memory. These results show the maximum and minimum possible latency reductions with prompt cache. The actual reduction in practice will fall somewhere between these 2 extremes, depending on how much of each type of memory is used. We also studied the latency of CPU inference. Our findings, shown in another figure, reveal that prompt cache can reduce latency by up to 70 times on Intel CPUs and 20 times on AMD CPUs. We believe this difference is due to the different memory bandwidths in the system setups: 5600 MT, SDDR5 RAM on the Intel CPU versus 3600 MT, SDDR4 RAM on the AMD CPU. As expected, the latency is higher for datasets with a larger proportion of uncached prompts, such as Trivia QA. Interestingly, CPU inference benefits more from prompt cache than GPU inference does. This is because the CPU has a much greater latency of attention computation, especially as the sequences become longer. To understand the impact of prompt cache on the quality of language model responses, we measured accuracy scores with the Long Bench suite. We applied prompt cache to 3 language models with different transformer architectures: Llama 2, MPT, and Falcon. The results show that prompt cache maintains the precision of the output. We used deterministic sampling, where the token with the highest probability is chosen at every step, to ensure that the results with and without prompt cache are comparable. Across all datasets, the accuracy of output with prompt cache is similar to the baseline. In theory, prompt cache should offer a quadratic reduction in TTFT latency over regular KV cache. This is because the overhead of prompt cache grows linearly with sequence length, while computing self-attention has quadratic computational complexity with respect to sequence length. We tested this theory on a synthetic dataset with varied sequence lengths, assuming all prompts were cached. We compared the TTFT latency of prompt cache to that of regular KV cache using an Intel i9-13900K CPU and 2 GPUs, NVIDIA RTX 4090 and A40, with the Llama 2.7b model. Our findings show that the latency of KV cache increases quadratically with sequence length, while the memory copy cost of prompt cache grows linearly. This means that the latency advantage of prompt cache expands quadratically with sequence length. This difference is more pronounced on CPUs than GPUs since CPUs experience higher attention computation latencies. As the model's parameter size grows, so does the computational overhead for KV cache. For example, moving from a 7B to 13B model at a token length of 3K added 220 milliseconds latency, whereas prompt cache added only 30 milliseconds. This difference is due to the fact that language model complexity also scales quadratically with hidden dimension size. Since prompt cache only reduces TTFT, its impact on the total time needed to receive the complete language model response decreases as the number of generated tokens increases. For instance, on the RTX 4090 with Llama 7B for 3K context, prompt cache reduces TTFT from 900 milliseconds to 90 milliseconds, while the time to subsequent token, TTST, remains consistent between KV cache and prompt cache at an average of 32 milliseconds per token, regardless of the token length. However, a quicker response time improves the user experience and the overall end-to-end latency. For example, with prompt cache reducing TTFT from 900 milliseconds to 90 milliseconds, 25 more tokens can be generated within the same timeframe. Section Summary. The authors evaluated the latency improvements of prompt cache on different GPUs and CPUs. They observed significant reductions in TTFT latency when using both CPU and GPU memory, with reductions ranging from 1.5 to 3 times for CPU memory and 5 to 10 times for GPU memory. Prompt cache also achieved up to a 70 times and 20 times latency reduction on Intel and AMD CPUs, respectively. Additionally, they found that prompt cache preserved the precision of the output, as the accuracy scores with prompt cache were comparable to the baseline. Section. Memory overhead. Let's talk about the memory requirements of prompt cache. The amount of memory it uses is directly related to the total number of tokens we store in the cache. To understand this, we need to look at both the prompt schema and the target language model. We've broken down the memory usage for each token in a table, assuming we're using 16-bit precision for floating point numbers. For smaller models, like Falcon 1B, if we were to cache a document with 1,000 tokens, we'd need about 180 megabytes of memory. If we have hundreds of these prompt modules, the total memory usage could be in the tens of gigabytes. This is still within the memory limits of high-end GPUs. However, for larger models like Llama 70B, caching a module of 1,000 tokens would require a hefty 2.5 gigabytes of memory for each document. This means we'd have to store the prompt modules in the CPU memory. Given these factors, we're looking into ways to compress attention states to reduce memory usage in the future. Now, let's look at how we can use prompt cache. We've tested it with more complex prompt structures and advanced features than those in the long bench suite. These include multiple modules in a query, union, and parameterization. These tests also showed that as we increase the number of cached tokens, the response time decreases. We compared the output of cached and non-cached generation to show that prompt cache maintains the quality of the output while reducing response time. We used the Llama 2.7b model and stored the prompt modules in the local memory, which is the GPU memory for GPU inference. Language models are often used to generate code, helping programmers either by assisting with or directly creating code. Current methods, like Copilot, usually focus on individual source files. But with prompt cache, we can extend this to multiple files by taking advantage of the modular nature of source code. For example, each class or function could be a separate prompt module. We've also used prompt cache for personalization, which is crucial for many recommendation systems. It's used in language model contexts like education, content recommendations, and targeted marketing. We've shown how effective feature-based personalization can be with prompt cache. Here, personalization is based on a set of features, each represented as a separate prompt module. Finally, we've used prompt cache for parameterized prompts. In a trip planning scenario, we used a schema with one adjustable parameter for the trip duration and 2 union modules to choose the destination. Users can reuse the template prompt with their own parameters, which reduces response time and maintains the quality of the language model response.